So what we're doing today is you're going to get a mixture of two solids. So I have all of the mixtures up here. So whichever one you get, there's a little unknown number located in the upper right. So just write that unknown in the appropriate spot in your lab. So what we're going to do is I'm going to kind of go over the pre-lab because there's some difficult calculations. And the pre-lab calculations are the same that you're going to do for the lab portion. So you can kind of just repeat them, but with your data, your numbers. So what we're starting with is a beaker. So you're going to mask this beaker when it's empty, dry, and then you're going to add some of that solid mixture to it. So what's in that solid mixture? It is potassium carbonate, so K2CO3, and then lead 2 nitrate. Okay, so what we're going to be doing is we're going to add water to that solid. When we add water to that solid, what's going to happen is instead of being solids, they're going to dissolve. So we're going to have, I'm going to put little AQs by them because they are now aqueous. When they become aqueous, what happens is they split apart into their ions. So now notice I added water, and then in this beaker I have little charged ions floating around. So now that they are separated in their ion form, they can react really fast. So we're going to see the reaction take place rather quickly. And what's going to happen, if you notice this structure from previously when you were looking at reaction types, it's a double displacement reaction. So we're switching partners. So when we're in the ion form, the driving force for this reaction is formation of a solid. So what's going to happen is, notice this is the product side of the equation, lead and that carbonate ion, so this Pb2 plus and the CO3 2 once they combine or touch each other, they're going to form a bond and they're going to precipitate out. Because this is actually a solid in water. It's not aqueous, it doesn't dissolve, it's not soluble. So when those two combine, it forms a solid, so we no longer have those ions floating around. Instead, we have a solid precipitate at the bottom that is that lead 2 carbonate. So the solid is the lead 2 carbonate. So we have the filtrate, the dissolved ions in solution that have K plus and NO3. And then we have the solid, which is lead 2 carbonate. Now, this isn't a perfect system. We're going to have an excess of one of them. So there might be some lead ions still floating in there that didn't have a carbonate to pair up with. Okay? So we're going to figure out what was in excess and which one was limiting by testing the filtrate once we separate the two. So over here we have our lead 2 carbonate solid. We have our aqueous potassium nitrate. And what we're going to do is we're going to set up a gravity filtration setup. So we've done this once before where we take a funnel, we get a piece of filter paper, and we flute it. So we kind of fold it in half, and then fold it in half again, and then it makes a nice little pocket. Okay, so you'll put this in your funnel to catch the solid. But the trick is you want to try to decant that filtrate, that liquid, off without getting any solid in the filter at first. Because if you put the solid in there right away, it's going to clog up the filter and you're going to be here staring at it for an hour waiting for the liquid to go through. So try to get the liquid off first, leaving the solid behind. Then when you get close to only a little bit of liquid left, you can just kind of swirl it and try to swoosh it all in at the end. Okay? So that's what decant means. It means try to get off the liquid without pouring the solid over. Once you get close to the end, that's when you will put the solid. So we're going to have solid lead 2 carbonate stuck in the filter paper. And then in the filtrate, in the liquid that we catch in a different beaker, we know we're going to have potassium nitrate, but we probably have one of the reactants as well in there still, because one of them was in excess, so there's extra of one of them. So we need to figure out which one is in excess. So we're going to take that filtrate and we are going to put a little bit of it in 2 different test tubes. So add, I think it says 5 mils in your lab manual, something around there. The amount doesn't matter because we're just looking at the reaction, like if a reaction happens. So you don't have to measure it out, just fill it halfway full maybe. Okay? So get 2 test tubes, put some of the filtrate in both, and then I have droppers up here of the two reactants. So you're going to take and add, I think, approximately 10 drops or so of the two reactants or two reagents to each of the test tube and see what happens. So if you, in one, you'll have the filtrate and you're going to add the potassium carbonate, this reactant here, and see what happens. And if there's a reaction, what you're going to see is just a cloudiness. Okay, essentially a solid's being formed, but it's not just going to clump out in like this perfect little solid chunk at the bottom. It's just going to look cloudy and white. Okay, so if you see cloudiness, that means a reaction happened, and it happened because the lead nitrate is in excess. So how do I know the lead nitrate is in excess if the reaction happened? Because if I take this K2CO3 and what's in the filtrate is lead nitrate, they'll react together again to form more of the solid. But if there's no reaction, that's because all that's in there is K2CO3. And when I add potassium carbonate to potassium carbonate, nothing's going to happen. So that would be the no reaction set. So that would tell me that the potassium carbonate is in excess. So you're using your results to figure out which one is in excess, and then by default, the other one is limiting. Does that make sense? Okay, so you're doing, excuse me, that to both test tubes, hoping to get the same results. You should get the same results in both test tubes, right? Either you'll see a reaction here and no reaction over here, or no reaction, reaction. So you shouldn't see a reaction happen in both. Something went wrong, or you added the wrong reagent, or something like that. Okay, so we're just double checking our results in that second test tube to make sure that we indeed got the correct one. And the same theory behind it applies. If there's no reaction, it's because we're reacting lead-2 nitrate with lead-2 nitrate and nothing's happening. Okay? So, with all this is just the observation portion. There's a lot of calculations that we have to do. So if you want to look at page 41, the pre-lab, we're going to kind of go through how to do all those calculations on that first page, because the calculations are the same for the lab portion that you're going to use with your data that you collect. So you'll notice I already have the balanced molecular equation up there. Hopefully it's balanced. Yes, it is. So that first part is done for you. And then the next two parts of number one is just asking you to do the ionic and the net ionic. So this is a little review, a little practice from before. So for net ionic, what they want you to do is the ones that have an AQ by it, the ones that are aqueous, which I forgot about this guy, he's aqueous, you split them up into their ions. The ones that are solid, you leave as a whole compound. So if you have the same ions on both sides, you cross them out. And whatever you have left is the net ionic. That makes sense. So, for instance, potassium is a +1 charge. You can figure that out from the periodic table. It's an alkali metal. There are 2 of them. I know that because of that subscript of 2 after it. For the CO3, that's a polyatomic, so I'm going to leave that together. That's carbonate. So it's CO3 2-. And then since lead-2 nitrate's aqueous, I'm going to split that up into its ions as well. There's 2 of these. So you split it up into its ions, and then you do the same thing to this side. You're not going to split up the solid into ions, though. So whichever ions match, you cross those out to get the net ionic. Okay, so I just started into the reactant side for you. You can do the product side and the canceling. All right, so let's look at the actual equations now. So number 2, we're going to use the molecular equation, which is this original equation with the states of the matter, to do some mole, mass, stoichiometry type problems. Go ahead and erase this so we can add something to it. So the first question is saying, okay, in one experiment you have 2 moles of the lead-2 nitrate. So it's saying I have 2 moles of this guy, and it's reacted with 0.75 moles of potassium carbonate. So they're saying this is the amounts that we added into the flask. So they want to know how much product is going to form. Product being this guy here. So this is a limiting reactant problem. What you need to do is figure out, okay, if I used all of this, 0.75 moles, how much product would form? And then do the same calculation, if I used all of this 2 moles, how much product would form? And whichever one formed the least amount of product, that's the limiting reagent. Because it means that one ran out, reaction can't go any further. Okay, so let's look at this a little bit closer. So I want to do, my steps are to take this potassium carbonate, 0.75, and I want to figure out how many moles of product is it going to form. That's my question. I'm going to do the same thing with the other reagent, the other reactant. I'm going to take lead 2 nitrate, that's 2 moles of it, and figure out how much product would form. So in order to figure this out, all you need is a balanced chemical equation, and that's what we have. So you're going to use what we call mole ratios. And the mole ratios, it's the coefficients in front of each compound that represents the number of moles of that compound. So what that means is 1 mole of potassium carbonate, because there's no coefficient in front of it, so I assume it's a 1, plus 1 mole of lead 2 nitrate is going to form 1 mole of lead 2 carbonate and 2 moles of potassium nitrate. So notice my ratio is a 1-to-1 between potassium carbonate and the product, and 1-to-1 for lead 2 nitrate and the product. So what that means is if I used 0.75 moles of potassium carbonate, it's a 1-to-1 ratio, so how many moles of product do I form?
0.75.
The same amount, 0.75. Same down here. We just said it's a 1-to-1 for the lead 2 nitrate and the product. So if I use 2 moles of it, it would produce 2 moles of product. So now we have to pick the smallest. So the reason we pick the smallest is because once this 0.75 moles of product is formed, there's no more potassium carbonate to make more of it. So it doesn't matter if I have tons of lead 2 nitrate left because I don't have anything to react with it. So since this one runs out first, that's when the reaction stops. So 0.75 moles of lead 2 carbonate is how much product is going to form. And potassium carbonate is the limiting then in this case. I don't know if it even asks you if it's the limiting or not. No, it does not. But it is the limiting, if you wanted to know. So I'm going to erase just this small section here. This is in your lab manual as well if you need to look at that. Because the next calculation, we're going to take that 0.75 moles and we're going to figure out how many grams that is of product. So it's a mole to gram calculation. So we have 0.75 moles of lead carbonate, and they're asking us to solve how many grams is that. So, moles to grams, in order to solve, you need the molar mass. Whenever we go between moles and grams, you need molar mass. So we have to figure out the molar mass of that guy. I'm going to do that off to the side here. So when you calculate molar mass, quick review, you want to make a list of all the elements present in the compound. So I have lead, carbon, and oxygen. I'm going to write those, lead, carbon, oxygen. And then next to them, you want to write how many atoms of each. To figure that out, you're using the subscripts. So if there is no number after that particular element, that means there's just one of them. So I have 1 lead, 1 carbon, and there's a 3 after oxygen, so that means I have 3 oxygens. So 1, 1, 3. You then take the number of atoms and multiply it by the masses on the periodic table. Which I don't know. I have my periodic table with me. I swear I saw one a minute ago.
Lead is 207.2.
Thank you.
And
Carbon's 12.
carbon is 12.011.
And oxygen 16, right?
Mm-hmm.
I don't use lead very often, but carbon and oxygen I use a lot. All right, so I think I already did the calculation, so let me fast forward to the molar mass. I ended up getting, so you multiply across and then add all of them together, and I got a total of 267.21 grams per mole. And the units are grams per mole. That's why we can use it to convert between grams and moles. When you guys do this in lecture, do you do the dimensional analysis way?
Mm-hmm.
Okay.
That's where.
So dimensional analysis way, I call it the railroad tracks. You kind of start by this plus sign. And what's always going to go in this upper left-hand corner is the number you're trying to convert. So in this case, I'm going to put 0.75 moles of the lead carbonate. And then I'm going to use this like it's a conversion factor. It's the same as saying 267.21 grams is equal to 1 mole. So I'm going to plug this in here so that the grams cancel, or sorry, so the moles cancel out, and I want the grams to stay, because grams is what I'm solving for. So in this particular case, the 1 mole portion is going to go on the bottom so that it cancels opposite sides of the horizontal line. And the 267.21 is going to go on the top. So moles cancel, and these vertical lines are basically multiplication lines. So I take 0.75 times 267.21 to get my grams of product. Make sure, how many sig figs are we looking at? 2, 3,
Yeah, 2 times.
2? Oh, because it was 2 from here?
That's the one, sorry.
That's kind of hard to do 2 sig figs on that one, because I got 200. You'd have to put it in scientific notation to get 2 sig figs. I'm not worried about it if you don't have the correct sig figs for that one. All right. Questions on this? So it's not really this one so much, it's part B. Part B is almost exactly the same calculations that you're doing in the lab. Because what they're saying is in the experiment, they had 10 grams of this original mixture. You're not going to have 10 grams, you're going to have somewhere between 1 and 2 grams. So you're going to have a smaller amount, but all the calculations are the same. So let's see how that plays out. So they're saying we have right here a 10-gram mixture of that. And what do they want to know? They say the mass that they collected of the product, this guy here, is 4.44 grams. And that's our initial goal, right? Once we get that lead 2 carbonate isolated on that filter paper, we're going to put it in the oven, dry it, and mass it so we can figure out how much mass we have of that. So it's the same steps. You're going to get your initial mass of your mixture. Once you're done and isolate the solid, you'll get the mass of that as well. So these are their results. Now they noticed that when they took their filtrate, so they had their 2 test tubes with their filtrate, the one that they reacted with, K2CO3, had no reaction. The one that they reacted with lead 2 nitrate, they did see a reaction. So it's this one. So since they saw a reaction, they can figure out that, hey, that means there must be excess of the potassium carbonate. So if the potassium carbonate's the excess, that means the other reactant, lead 2 nitrate, has to be the limiting. And this is important because you need to know which one's the limiting in order to do the next calculations. So this next calculation is a big one because they want you to go from the grams, oh sorry, not from that grams, from the grams of the product, right? All the way backwards to the grams of the limiting reactant. So which one did we say was limiting?
Lead.
Yes, so limiting is lead nitrate. So this is important because we're going to need the molar mass of that guy, which luckily, no, we didn't calculate it yet, which we'll need to calculate when we do this next problem. Because what they want us to do is start with this. So they want to go from grams of lead carbonate, from grams of product, and they want us to figure out the grams of the limiting. And we said the limiting was the lead nitrate. Now, we can't go from grams of one compound to grams of a different compound in one step. What we have to do is we have to convert it to moles first, because then we can use this balance equation, like we did earlier with that 0.75 moles, to get to moles of a different element or compound in that reaction. It's kind of like a side step. So, we have the grams of the product, 4.44 grams. We're going to convert that to moles using the molar mass, right? Whenever we go between grams and moles, we use molar mass. So we need the molar mass of this guy, which we calculated in the last problem, so at least that makes it a little easier. Now, once we have moles of product, then we do that ratio. So the ratio of what? So we're comparing lead 2 carbonate, this guy, so we're looking at the coefficient in front of him, to lead nitrate. And it's just a 1-to-1 again. Okay, so that means it's going to be the same. Whatever moles we get for the lead 2 carbonate, it'll be the same moles of the lead 2 nitrate. Now the last step, we'll need molar mass again because we're going from moles to grams. Okay, so quite a bit of information we're going to need here. So I'm going to erase this part to give me room. So we need molar mass of lead 2 carbonate. What did we say that was? 250 something? 60?
67.21.
Thank you. The mole ratio is 1-to-1, so we can technically skip that step. Because it's saying 1 mole of lead carbonate is going to equal 1 mole of lead nitrate. So that's this middle step here. And then our last step, we need the molar mass of the lead 2 nitrate. So same steps as before. We have lead, nitrogen, oxygen. I have 1 lead. How many nitrogens do I have?
2.
2, yep, because of that 2 outside of the parentheses. How many oxygens?
6.
6. So what did you say this was? 207? I already forgot.
2.
207.2.
2. Nitrogen's 14 something. Right?
14.
It's just 14.00?
0.007 is what.
Okay, so it would be 0.01 if I rounded it to 2. Okay, so multiply across and then add them all together. Did I do this one ahead of time? I did. Double check my work though. I get things wrong too. 331.22 grams per mole. Because you're going to be using these same molar masses for your lab calculations, so you might want to double check and make sure I actually calculated them right. All right, so those are the 3 pieces of information we need, so now we can start our dimensional analysis. This is going to be a longer one because we have several more steps. It's not just a one-step one. Find a better marker here. So we want to start with the grams here of the lead 2 carbonate. So that was 4.44. Next, I'm using the molar mass of lead 2 carbonate, this guy here. Am I going to be multiplying by 267 or dividing?
It's gonna go on.
Fine, wait,
Yeah, it's going to go on bottom. We're dividing because we want the gram portion on the bottom to cancel. So that'll put the gram on the bottom and then the 1 mole portion on the top. So grams of lead carbonate, canceling. So now I'm here, I'm at moles of lead carbonate. And we said it's a 1-to-1 ratio. So we're really not doing a calculation here, we're just canceling out one compound in place of another. So just in case you're wondering what it would look like, it looks like this, so that we can get rid of the moles of lead carbonate. Now we're here in moles of lead 2 nitrate. So our last step is molar mass again. So for this molar mass, what are we doing? Top or bottom? For that 331? Top.
oh yeah,
Top, yeah. 331.22, because that's the gram portion. And that'll put the mole, the per mole part, on bottom, so that the moles cancel. Now our units are going to be grams. So to solve, we multiply all the way across and divide by what's on bottom. So this is going to tell us how many grams of lead 2 nitrate were in our initial unknown sample. So, what did I get, 5.50? I think we need 3 sig figs. Yes. So if we know how many grams of lead 2 nitrate, we can figure out grams of potassium carbonate, because the whole sample was 10 and only 5.5 of that was the lead. So that means the rest of it had to be the potassium carbonate. I'm sure you probably already know how to do this equation, but I'll show it anyway. For finding the percent of the limiting reactant, so once again, we said that the lead 2 nitrate was the limiting, so they're asking for the percent of it. You're going to take this mass amount, so percent, you're going to take this mass, so the mass of the lead 2 nitrate, and divide it by the mass of the sample. Don't forget to multiply by 100 to get it in the percent. So mass of the lead 2 nitrate, we have it here, the 5.5. The mass of the total sample they started with was 10. And then they ask you to do the same thing with the other reactant. And so it's the same steps that we saw here, except for you're replacing the numerator with the other reagent. Kind of a lot of calculations.